All right, so now that we know all about centripetal acceleration, now we can use the fact that F equals ma. Right? We can figure out centripetal force. It's just now the acceleration is the centripetal acceleration that we just found, which is just v squared over r. And that means we can write that just like that. So that's really what that is. Centripetal force is the net force that causes centripetal acceleration. The word net is just there to let you know that there could be multiple forces on an object, but if the net force is toward the center, that's going to give you your centripetal acceleration or what you want. So here's a little example of this. An astronaut spins a yo-yo, which has a mass of 100 grams, around 180 times per minute. The diameter of the circle she spins it in is 0.5 meters. What is the tension in the string? So the tension is just going to be whatever the force is in the string, right? Basically, we just want to determine what this force, if you're looking at the picture there, what that Ft is, right? The force of tension toward the center. Okay, so the first thing I would get here is the speed, right? V. At this point, like it's written in here as a vector there, but that doesn't really matter because it's really just the speed I want. It's just going around, so its velocity is constantly changing, but I just really care about the numerical value, what that actually is. So I can look at, so I know that V, or the speed, is just distance over time. And the distance that it's gone, well, when it's got this is a circle with a radius of 0.5 meters. So when it goes in one circle, right, the circumference of the circle is just 2 pi times by r. But it does this 180 times per minute. So let's just look at over 1 minute. It's gone a distance of that times 180. And 1 minute is 60 seconds. So that means that the speed is 4.71 meters per second. All right, so I'll write that in there just to be more clear with what we're doing. Now that I know V, I can go to centripetal acceleration. I almost feel like I'm following that strategy here I've told you before, where sometimes it's just, what can I do? Right? And I look at this and say, well, I can figure out the speed. Now I can figure out the centripetal acceleration, right? It's just V squared over R. And V I just figured out is 4.71. So I'm going to square that and then divide by the radius of this, which again is 0.5. And that tells me that the centripetal acceleration is 88.8 meters per second squared. Now I can go to what I know about forces and say, well, that means the force that she's applying on this thing, which we can call a centripetal force because it's going to be towards the center of this circle, is the mass of the yo-yo times AC. Oh, sorry, my bad. I did write in the wrong number here. It does say that it's a diameter of 0.5. So yeah, that means this should have been 0.25, which I did actually use before when I worked out that number. Just looking at it now, I just glossed over it. And so we can still use that number. We have a mass of 100 grams, and 100 grams is just 0.1 kilograms times 88.8, which means the force being applied here is 8.88 newtons toward the center. So we've just looked at centripetal force, right? Note that this is a real force, right? Centripetal force is real. You apply a force toward the center of an object or towards the center of some circle, and you do cause that acceleration. We looked before at what that acceleration was, and That's an important fact about this. This is real. Centrifugal force and Coriolis force. These are fictitious forces. They are not real, but they may feel real depending where you are. So I actually have a little bit of a video that kind of shows this. This is what these pictures here are from. This is from Science Click, so it's link on the course plan. And this is just showing. So the idea here is you've got, let's say, some astronauts out in space or something like that. One way to give them some artificial gravity is to have some sort of round shape like this and have it spinning around, right? And so this is just looking at what would happen if the astronaut or one of them was holding something and dropped it. So you can see, and this is just, it's freeze framed right now, but it's saying if this thing is, so because it's spinning, you would feel a force toward the outside. And this is kind of like what the ball would have felt when I rolled it around earlier. So here is showing you if you have a ball, right? The astronaut's holding a ball and lets it go. What happens, right? Well, just like the ball on the pie plate I had, right? It's going to follow a straight path as soon as the astronaut lets go of it, right? But this is from the astronaut's point of view. It's going to appear to fall straight down, right? Perhaps this big circle that he's in that's going around is so big that he doesn't even really realize. Just all the astronaut knows is they're experiencing a force toward the floor. And when they drop something, it appears to fall straight down. But we actually know better, right? We actually know that, right? It's not that. It's just that as soon as he lets go of the ball, it follows a straight path. So for the Coriolis force, if you're looking at this, you see how everything here is represented with arrows, and you can see how that basically what this is trying to show is if you pick a spot, right, and just pick one of these arrows here or something. Okay, so pick a spot, like let's say right here, right? How fast would that spot, what would be the velocity at that spot right now, right? Well, it's pretty close to the center of the circle where it's spinning. So you could say, well, the velocity is it's just a little bit, right? It's not going too fast right there. But as you move out, right, as you move, let's say down here, right, this spot would be going faster because it's farther away from the center of the circle, right? So in this both of these spots I just did, right, in the same amount of time, they're going to go, this one's going to go all the way around and complete one circle in the same amount of time that this second one would complete a full circle, right, which is definitely a much greater distance. So it's going to be going faster, it's going to have a faster velocity. And we could do the same thing for some other point, right? The farther down we go, we can say, okay, it's got a, right, the velocity increases as you move farther away. So that's what those arrows are showing. And so give that a second. So now the question is, okay, what happens if this astronaut throws the ball up into the air? Right, you can see the ball is getting closer to the axis of rotation, right, to the center. And so it's going to appear to curve away from him because the ball still has that greater velocity, right? Because when he threw it straight up, right, it still has that, circular component to its velocity, which is greater than the components above it. So as it goes up, it's actually going to move to the side. And so from this astronaut's perspective, then, right, why does this thing, when they throw it straight up in the air, why does it appear to go on some sort of arc like that? And so the astronaut might say, well, there's some force, let's call it the Coriolis force, that whenever you throw something up in the air, it makes it go forward for some unknown reason, right? It's just there, it's a thing. And so, as with the other one, it is a fictitious force. So anyway, back to the note. That's really what I was trying to capture a few pics of this here just to show you the centrifugal force. So this is a force in a rotating non-inertial reference frame that acts opposite the direction of the acceleration, right? So like I said, this astronaut might feel like, well, whenever they drop a ball here, right, it accelerates straight down. There's some force that pulls it towards the floor. But we know that's not actually the case at all. It's actually that the ball, just as it showed here, just as soon as it's let go of, it follows a straight path, right? And the Coriolis force, usually this is something you see more on Earth for the same reasons that we just saw. So it's a fictitious force that acts perpendicular to the velocity of an object in a rotating frame. So if you look at something like Earth, right, it's similar to what we just looked at with the circular spaceship or whatever. Um, if you think about it, right, at its equator, the Earth, right, is it's going faster, right? If you were just looking at the how fast something is going on the surface of the earth around the earth, it's going to be going faster at the equator than it would be up here. And that's just because it's at the top here closer to one of the poles. It's not as far from the center or axis of rotation, so it's not going as fast. But then what happens if right at the you say fire some projectile from Earth's equator, but you try to fire it straight up like that? Well, the horizontal component of its velocity remains the same. So as it goes up, or gains more longitude, latitude, as it gains more latitude, it goes up. Then right, it still when it gets up here, let's say it still has this much velocity in that direction, right? Trying to get it to go around. But up there, it's not, that point on Earth isn't rotating as fast. So it appears then to follow a trajectory. Well, it appears it follows a trajectory that looks more like that. It would actually be curved as it went up, but this is just showing uh, some angular velocity. So you get something that looks more like this. We see this with winds and stuff like that as they go, or prevailing winds and whatnot are somewhat created because of this effect. But note, it is considered a fictitious force because once again, there's nothing actually pushing them in that direction or whatever, right? They're really just preserving their own velocity. All right, let's get to a real example. Um, okay, a few years ago, instead of teaching summer school, Mr. Brown tried driving a bus. His only passenger trip, which led to multiple customer complaints, the coefficient of static friction between the tires and the road was 0.65. Okay, seemingly disconnected, but okay. He expertly negotiated a turn of radius 200 with a banking angle of 30 degrees as fast as possible before the tires slipped. So we want to determine what the speed was then, right? How fast was I going around this thing? Maybe not the best diagram to kind of show this, but I tried to start a free body diagram. So often with things on an angle like this, I would angle my axes, right? Because it's totally arbitrary and always up to you with what's positive x, what's positive y. You just want them to be perpendicular. However, because I know this thing is going around, presumably, right, there's some center line here, some axis of rotation like over here, and this thing is kind of going circular around it, right? It just happens to be on some banked angle. So because this thing is accelerating in that way, I think it's easier to just let that be my x direction. That way, when I want to calculate the centripetal acceleration, I don't have to break it into components. So I define it this way. So I drew the force of gravity, which we know is directly down. And I drew the normal force. So this block I've got here is the bus. We're told that it's a bank angle of 30 degrees. So we've got that. We know for this, I drew the acceleration, and we know Turn radius is 200, so we know for this. Oh, I'll write that in there as well. R equals for the turn, the radius of this circle that this thing's going around. The only force I haven't drawn is friction. Absolutely. Okay, so what direction is friction? You've got options here, right? Which of these four directions would friction be in? No, this is a really funny one because absolutely, I think someone commented here that friction is it always opposes the motion, right? So it should always be parallel to the surface, right? Just like the normal force should be perpendicular to the surface, friction should be parallel to the surface. So that tells us we're probably looking at 1 or 4 here. Even though the acceleration is toward the center, but yeah, the friction should be 1 or 4. Now we really got to think about, well, we know it opposes the motion, so which direction is the motion? Now, if I told you that all I did was park a bus on an incline, right, then I think the answer here would be pretty obvious, right? It would be 1, right, because the bus would want to slide down the hill. Friction would be the only thing, right, preventing it from going in that direction. It would be the only thing that could counterbalance the x or the down the slope portion of gravity. But it's got a lot. This is different though. It's got a lot of velocity. So if you think about this, now imagine the bus is going really fast, and maybe it's even easier to kind of look at this bank angle and think, well, what if friction wasn't there, right? What if all of a sudden, right where the bus is now, and I know this is not the best drawing, you just have to sort of look at it like that, right? Like it's on this part of a ramp or something, and all of a sudden it's pure ice, right? And yeah, this ramp curves around or whatever, right? But relative to the height of the ramp, would the bus go up the ramp or down the ramp? If all of a sudden going really fast, it hit ice, would it fall off the top of the ramp or would it slide down to the bottom of the ramp? It would fall off the top of the ramp. It would slide right here and go way off the ramp. Terrible tragedy. Fortunately for my adventure here, that was not the case. Lots of friction. So in this case, the bus actually wants to slide and follow this path here and go off the ramp that way. So that means friction is actually in the opposite direction, right? You would think. So that means it's actually direction 4 here where we're going to have our friction. Let's see if I can sketch this. Because we've defined x and y to be the way they have, I actually should resolve this then, or look at. I want to break this up into its components. Now, if this is going to be 30, then that means I should have the same angle inside here. And again, the way I always just kind of think about it is, it's a little bit of a cheat, but it's saying, well, if this incline was 0, right, the angle here would also be 0. So as I increase this angle here, that second angle increases as well. And then the other force I would have to resolve would be the normal force. Which this would also be 30 degrees. And so I can look at this. Now this is the opposite side, so this is going to be Fn sine, and this will be Fn cos. And I can do the same for friction. This will be, it's closer, so it's cos. And that side there will be the force of friction, sine And that's essentially all I need as far as a free body diagram goes. Um, I can look at now. This thing is not moving in the y direction at all. Again, remember the centripetal acceleration is over here in that direction. So that means when I look at this thing, if I look at the sum of the forces in the y direction, that should equal 0. Now, it might seem a bit odd. I'm not given some things that you might think you would want. I'm not given the mass or anything like that. But even when you get stuff like that, just roll with it. No pun intended. Um, so if I look at this, I've got in the y direction Fn cos 30. Right, that's this upward one here. And then I've got the downward component of the force of friction. So minus the force of friction sine 30 degrees and minus the force of gravity. And all that should add up to 0. One thing, and I put the little notes up here just ahead of time because I use these numbers often, right? Sine 30 or 60. So just as if you remember the 1, 2, root 3 triangle, remember the sine of 30 is 1/2. The cosine of 30 is root 3 over 2, just from the sides of this triangle. And especially if you get a complex problem like this where the numbers don't cancel, it could be easier. So this here then is just Fn times root 3 over 2 minus the force of friction. And I think I can actually replace that with mu s. The force of friction is just mu times the normal force. In this case, it is actually mu s because it's not slipping at all. It's not going down. And the sine of 30, we said, is 1/2. Minus the force of gravity, which we know is mg. I don't know that, but that's okay. I've got Fn in the first two terms, so I can factor that out. It gives me Fn and root 3 over 2 minus mu s over 2. That's just multiplying mu s by 1/2. And I can take the mg to the other side or add mg to both sides. And that means I can figure out that means Fn equals mg divided by root 3 over 2 minus mu s over 2. I suppose if I wanted to, I could remember with anytime you've got a fraction, you can always multiply or divide the top and bottom by anything as long as you do the same. So we could multiply the bottom by 2 or multiply the bottom by 2, which gets rid of the 2's here. And then we could multiply the top by 2 as well. And so that just simplifies our lives a little bit. So now I can say if I sum all the forces in the x direction, that should equal mac, since it's only centripetal acceleration that it has. And if I can kind of look at this diagram a little bit, so I've got the force of friction, or the x component of the force of friction. So that gives me force of friction cos 30, and that's what I've defined x positive to be that way. I've also got part of the normal force in that direction, Fn sine 30 up at the top. And that all then equals mac. So the force of the force of friction is same thing, mu F, mu S Fn, and cos of 30 we said is root 3 over 2 plus the normal force times sine of 30, which is 1/2, equals MAC. Still not a lot I can do there. Once again, though, I can factor out the normal force. And that leaves me with root 3 mu S over 2 plus 1/2 equals MAC. A little bit of math, but and I suppose at any point there I could actually replace, since it's centripetal acceleration, with V squared over R. And have I got room down there? Yes, I do. Now I've already, on the other side, I already worked out an expression for the normal force, so I can actually replace that in the other one. So I can put that in there. So instead of the normal force, I can write 2 mg divided by root 3 minus mu s. And that equals root 3 over 2 mu s plus 1/2. And that gets me here. Well, now I see why I didn't have a mass, because I didn't need one. Because if you look at both sides of this equation, you will see the mass term. So since that's there, I can just divide both sides by m or cancel that out. I've also got an r on the bottom of the second one here, so I can multiply. Let me just do that. Multiply both sides by r, because ultimately I want v, right? I do actually have mu s here, right? That was given to me as 0.65 up at the top here. All right, so putting in the numbers for all those, right? So basically I've already got v on one side all by itself. I just switch sides because it doesn't really matter. And then take the square root of both sides. That gives me all this, which is just a bunch of numbers you can put into a calculator. And that gives you v equals 62 meters per second. Which I think is about 220 some kilometers an hour. So not bad. I think they had an exciting ride.